Hi everyone, this is Nick and I's presentation on linked lists. Music by Nick.
Hello, this is a presentation on linked lists.
Fantastic. Okay, so a linked list is a type of data structure, much like an array or a vector. A linked list is just another method of storing information, and there's a few functions attached to that. You can add or delete items from a linked list, and you can write out the contents of a linked list to disk. A singly linked list is the simplest type of list there is. There's other types like doubly linked lists and circular linked lists, and I'll go on to those later on. Just to give a comparison between linked lists and arrays, arrays hold all information contiguously in memory. So when you declare an array, everything's held in one location. All the cells and the information inside the cells are all stored in one big block in memory. You can't easily insert or take away cells from arrays without, well, to be honest, without rebuilding the entire array. A linked list is a little different. A linked list is like a chain, so you can always add a link or remove a link from the linked list as you go along. So the size of the linked list doesn't have to be declared beforehand, and also it's not held contiguously in memory. So a linked list, you can have one part of a linked list in one area of memory and another in another, and they work just as well. So here's an array of 6 elements, and as you can see, all 6 cells are all held contiguously in memory. They're all one after the other, like so. And when you declare an array, you have to declare the size beforehand. So with a linked list, that's not the case. So with a linked list, when you start a linked list, you have a node, and you have a node. The node has two characteristics. It has a data, and it has a pointer, and the pointer points to null, and null's just a special value that says that there is no more nodes after this. This is the first one and the only one. When we add another node, this new node, isn't that good? This new node now points to null, and the first node, the tail, now points to the new head, and the new head points to null. You can keep adding nodes as you go along. You can add nodes to the beginning or the end or in the middle, and every time you add another node, the node previous to it now points to this new node. Or if you add it to the end, for example, the last node, the previous head, now becomes is no longer the head, and the new node is the head, and the old head points to it, if that makes any sense at all. Oh, you'll see this later on anyway. Okay, so there's a range of different functions you can use with linked lists. So you can add and delete and access nodes. You can add a node to the head. You can add a node to the beginning, and so on and so forth. And you can construct and destruct linked lists as well. So just to show you a few different examples, there's a doubly linked list, and the doubly linked list is slightly different. In this case, each node has 2 pointers, and one pointer points to the next node, and one pointer points to the previous node. And of course, you have your datum in the center, whatever you want to store inside the linked list. You have an item called a sentinel node, which is sometimes referred to as the first node, but it's sometimes not used. It's all to do with the searching algorithm, as far as I'm aware. So another type of linked list is a circular linked list. So in this case, with a circular linked list, it's like a double linked list, except the head and tail now point to each other. So here's our first node, and as we keep adding nodes, you can see they point to the previous node and the next node. But the head and the tail now point to each other. So in another regard, that's the only difference between a doubly linked list and a circular linked list. Now, just to give you an example here, if you were adding a node to a singly linked list, here we have node A and C, and the last node points to null. But we've added another node. So this new node now, to get this new node to be attached to our linked list, we have to have the new node point to C, and then we dereference C from A, and now A points to B instead. So here's our A, B, and C. So isn't that good? Now, this took me quite a while, so I hope you appreciate it. Here we're going to delete a node. Now, deleting a node, there's more steps to deleting a node than there is to add a node. So, and generally we use an iterator to do this. So first of all, the iterator must point to the node we're going to remove, in this case C. So, whee! So C gets deleted, blink, and now node B has to point to node D, and we've got rid of our node. But we have a problem. We have to do something with the iterator. We can either remove the iterator altogether, or we can have the iterator point to the next node, or the last node, like so. Isn't that good? So, just in conclusion here for the presentation, Nick will take you through the code after this. There's flexibility in a linked list that you don't have with an array. You can insert or take away nodes in any position. You can put it at the head or the tail or anywhere in the middle. It doesn't take up contiguous space in memory, so I'm not entirely sure about this, but I think it's something to do with the fact that you can search through a linked list slower than you can with an array, but in some cases it's much handier when a linked list doesn't take up contiguous space. So an array has the advantage on that one, and the size doesn't matter. The size of a linked list can be any size. You can keep adding or taking away as you go along. And the cons, well, if you're looking through the code you've all done yourselves, like, lists can be a lot more complex to access than arrays can. Okay, thanks very much. I'm just going to hand you over to Nick now.